Eccoci, buonasera. Good evening, everybody. Can you hear me? It's a usual question. Okay, thank you. All right, good evening, everybody, and you're welcome virtually to the Istituto Italiano di Cultura in Berlin, Germany. My name is Vincenzo Fiorentini, and I'm a science attaché at the Italian Embassy, and I'm filling in for the director of the Institute who cannot be with us today. So tonight here at the Institute, virtually, we will be presenting a new book, The Human Computer, which is this sizable tome here. It's an actual physical book, some 370-something pages, published by Quaternion Books, which is a publisher we will have more to say about in a second. And we'll be discussing this book with three of its four editors and curators, who are four young astrophysicists: Elena Sacchi, who's with us today, Valeria Korol, who is also with us today, and Yuri Kavecki, who is also with us today. And the fourth one is Alessandro Patruno, who could not be with us tonight. So the schedule is as follows. We will have short presentations by each of our guests, and then some discussion, perhaps with questions from the audience that can be posted in the chat, I think. Right, so the video recording will be made available probably before Christmas on YouTube, on the YouTube channel of the Institute, and I guess on other sites, like connected sites like the Embassy or the institutional sites of our guests. So by way of introduction, very briefly, so the book is essentially a cross-section of the work, of scientific work of a peculiar character. Katherine Johnson was a very gifted mathematician who was, well, precisely what the title says. And she was a human computer, meaning a human, of course, who did computations by hand or by mechanical calculators back in the 1950s into the 60s and early 70s on orbital motions and other problems relevant to space missions. She was one of many who worked at the Langley Space Center in West Virginia. It's an operation center of NASA. Now, the book includes a readable introduction, not too technical introduction, about the space race, say, in the era in which Johnson was most active, like the late 50s, early 60s. And then it collects six papers by Johnson. Perhaps you can see the yellowish, maybe not. So the yellowish part are these bulky scientific papers that have been, I could say, transcribed or transmogrified by our guests from what I imagine must have been barely intelligible copies or something of the 60s into a modern graphical layout that is, and new figures and so on. Plus, the editors have provided a detailed commentary on each paper. On occasion, it's more extensive than the papers themselves, including mathematical information for those who are into mathematics. Okay, so I guess the general message of this book is about the fact that Johnson had aside from her excellent performance as a mathematician and a scientist, had a difficult career because she was a woman, essentially, in the 50s. That's the main issue. Plus, she was a woman of color, which didn't make things any easier in the American South in the 50s, you can imagine. So I guess the issue that this story brings up prominently is the subordinate role of women in science in those times. I think Johnson was the first and perhaps the only among her colleagues who actually got to even sign her scientific works. So, which is, this obviously reminds us of other stories like Rosalind Franklin and Jocelyn Bell and so on, not so extreme as this one, but still has a, it smells of this questionable custom of using, if not exploiting, the work of subordinates, assistants, and students, and so on, without due recognition, which is actually which is cross-sectional, doesn't have to do with sex really. So luckily, well, these are mostly, these issues are mostly a relic of the past, that still, reminds us of the importance of tapping into the intellectual abilities of women, which we will have a couple of examples tonight. And of course, to give credit where credit is due. So a final comment is about the publisher. So the publisher is essentially a startup that involves the curators, the editors of the book themselves, and has reissued a number of lesser-known classics of science, as this original project we are discussing today, and has a new project ongoing about the women of Bletchley Park. That is the code breakers, the British code breakers that worked at the site that is well known because Alan Turing worked there. Okay, so I have bored you enough, I guess. So let's move to the contribution of our three guests. We will start with Valeria, I understand. Valeria Korol works at the Max Planck Institute for Astrophysics in Garching. Before that, she was in Birmingham, UK. And before that, she obtained a PhD in Leiden. And before that, a Bachelor of Science from Genoa University in Italy, and a Master of Science from Bologna University in Italy. So she's practically Italian, although I guess of Ukrainian origin, if I'm not mistaken. So, okay, Valeria, you have the floor.
Thank you. Let me share my screen. Okay. So, since I'm the first of the guests to talk, I'm going to follow up on some of the points that Vincenzo has just mentioned to us, and let me start by introducing you the Quaternion project. So this is in practice a small publishing startup which was funded and run by these four enthusiastic people: Alessandro Patruno, Flavio Pietrobelli, Marta Mazza, and Jenna Barton. So they all have a science background, and they are very passionate about communicating science. So what they want to do with the Quaternion project is to challenge the traditional scientific publishing business model that uses authors' intellectual work to generate the revenue, and instead with the Quaternion, the idea is to use authors' work to generate value. So practically, the idea behind all this is to collect sales revenue from the book and use these funds for projects that promotes inclusion in the STEM field, and that can be, for instance, some science scholarship for underrepresented people, then summer schools for students in developing countries, and even just by publishing books on this topic. The idea is to stimulate public discussion on the overlooked scientific contribution from minorities. So their first original publication was this book, Discover the Solar System. And this is basically, the Outreach Classics, but it is based on the up-to-date discoveries that has been done by all of those space probes that we have been sending to explore our solar system in the past decades. So practically this publication was meant to test the waters, to understand the publishing chain, and to test the business model. And as Vincenzo mentioned, they also republish some of the existing science classics. So for instance, One of my favorite are the notes by Ada Lovelace on the sketch of the analytical engine invented by Charles Babbage. The engine, which was basically the first analytical computer, was never realized, but Ada, thanks to these notes and her work, is considered the first computer scientist and the author of the first computer algorithm in history, which is part of her notes. In this presentation, we are going to focus on the most recent of the original Quaternion books, which is The Human Computer, and it is a tribute book to Katherine Johnson that, as you may know, is one of the most famous Afro-American mathematicians, and she's famous for contributing to the NASA success in the early days. And basically, as Vincenzo has already explained, the book consists of her original scientific reports that has been retyped and restyled, and for instance, also the figures has been regenerated based on the original ones in a high resolution digital format. And each of those reports we accompany with some commentary that is aimed at the non-scientific reader. And basically we try to guide the reader into the logic behind this calculation, some of the mathematical passages, and also to put it in a broader constant to be able to understand the significance of a specific report. So I also wanted to go back to the title of the book, which is The Human Computer, right? And we call it that way because that was Katherine Johnson's profession. And I know it may sound odd nowadays, but the human computer was an actual profession for several centuries, from the about 15th century up to mid 20th century. And this was people, they were typically working in groups, and they were undertaking long, difficult mathematical calculations. And they were managed in a way that these big calculations were split in smaller chunks that could be done by a single person in parallel. So here you see an image, a photograph example of the NASA's human computer division. And then in the mid-20s, precisely the need for speeding up the calculation for more difficult problems that came up after the Second World War led to the creation of the digital computers as we know them today. So Katherine Johnson was perhaps the most famous of the human computers, at least in the recent history. And this is thanks to her important work for NASA. So she was calculating, for instance, the flight's trajectory of the astronauts, including Alan Shepard, one who was the first American in space. Also the re-entry trajectory of the John Glenn, and that was featured in the Hidden Figure movie that came up a few years ago. She was also computing trajectories and the moon landing for the Apollo missions, and when the Apollo program terminated, she contributed to the Space Shuttle program and the Earth Resources Satellite. So the book includes some of these famous reports, but also her less known works. For instance, the work on the stability of the aircrafts, determination of the moon's gravitational potential, which was paramount for the moon landing, right? She developed space navigation methods for manned mission, and she even studied the response or the control of the antennas on the spacecraft. And we are going to go in detail on some of this. So I personally overviewed those chapters that looked at interplanetary navigation. And I have to admit that this is conceptually very difficult problem, because when you are navigating in space, right, you're in the pitch dark, you have no landmarks, and you have very little stuff that you can use to compute your position. So these were conceptual works in which Katherine Johnson explored how solar planet systems, and of course later on the stars, can be used, their position, for instance, their sizes, the angles between different bodies of the solar system can be used to determine the position of the spacecraft. So to do that, she had to study the missions. These missions has to be studied ahead, of course. So for a given trajectory, she was computing, for instance, here you see a little sky chart. And you see the trajectories of the Sun, Venus, and the Saturn as they evolve across the sky, as seen by the astronaut on the spacecraft during the mission. So these little ticks with numbers indicate the number of days that passed after the mission started. And here you see an example of a plot that in which she shows how the angular size, or the size of a planet as seen by the astronaut, changes during the flight. For instance, in this example, it was a mission to Mars. So of course, if we follow the Mars line here, it increases during with time, and as the mission moves away from the Earth, of course, this one, the size of the Earth would decrease as we go farther away. And most importantly, and life-saving, were understanding how and which angles between solar system bodies could be measured in a way that these were the most precise measurements. Once all this preparatory material has been done, the astronauts on Apollo missions actually perform those measurements using a sextant. So this is the instrument used in navigation for measuring angles, and this instrument was specifically designed for the astronaut and built into the Apollo spacecraft, so that the angles could be measured. They were typing in the measurements in the onboard computer, and then the computer would give you the position of the spacecraft. So this was really life-saving for at least 2 of the Apollo missions. So Apollo 8 and famously Apollo 13 missions, during which the mission was aborted because of the problems on the spacecraft, and the astronauts had to compute their re-entry trajectory based on their own measurements done with the on the fly. So I will now pass the stage, open the stage for Yuri. Let me stop sharing the screen.
Yep. Thank you, Valeria. Let's start sharing my screen. Okay, so let's say my goal here is to really show how versatile, how diverse was the work and the contributions of Katherine Johnson, because we heard space navigation and exploration. We're going to hear more, but she really worked on many different topics, as it was mentioned, right? Stability of flying a plane or controlling an antenna in space. And what's really striking is that she used a wide variety of methods, right? I mean, they had to solve equations, they used linear algebra, she also used early computers. And to be honest, when I started reading the paper, I had some troubles. I had to learn, I had to document myself to understand. But luckily, they're written quite clearly. So in the end, I understood, I hope. Oh, well, just to give you an example, this is one of the figures I had to see, and I was a bit puzzled. I was saying, what am I looking at? But I mean, in the papers it explained, and this in particular is about maneuvering an airplane. So NASA is the National Aeronautics and Space Administration. So they developed also planes, basically. And this is a little model they had, and it's actually a model of the plane on which Katherine Johnson's worked. And she worked in this particular case about the stability of the maneuvering the airplane. Basically, when you're turning the airplane, when you are doing your trajectory, the calculation was how hard, what's the limit, how sharp, for example, can be my turn before the airplane goes out of control. No? This is important if you want to go fast and efficiently and so on. And to give you an idea what she used, well, they combined the hydrodynamics equations, which basically control how fluids move, but specifically tailored to how the air, for example, moves around planes. And they changed this equation, they perturbed it to obtain what are like oscillation or deviation, basically to check the stability. For example, you are turning, the plane starts shaking, is the shaking limited or it's going to go out of control, is the plane stalling, for example. No? And a funny detail is that to check for specific airplanes, you have to plug in the data of the airplane. And at NASA, they actually had these models and they put it in wind tunnels and measure the parameters they need for these equations. And then with the equations and the data, you plug everything together and you can determine, you can measure these limits, the stability of the maneuverability of the plane. And this is exactly what the work of the paper that I read was about. And they have actually a very complicated algorithm, very elaborated, because they have to solve the equation, they found many solutions, they have to choose basically automatically the only physical solution, and then they have to elaborate on this solution to check which ones are stable, which one would make the plane crash, for example. No? And this leads to this kind of figures, but after you read the paper, they make a little bit more sense. And these are basically parameters of the plane. Now, these are the angle between the air of the plane and the air and the plane, the wind and the plane. And for example, the angle of the movable part of the wings will determine how you turn. And some of these solutions are stable, some are unstable. And the problem is when a stable solution crosses an unstable solution, then there is a high chance that the plane goes out of control. But she wasn't content with that. She went on, she worked on other things. And one of those was controlling a space antenna. And you may wonder, why do I want to put an antenna? Or perhaps people wondered about that at that time. Maybe now, no, because now we have cell phones. We know that for communication, for example, having an antenna in space is useful. But you can also use it as a telescope, like a radio telescope, no? Nowadays, we put optical telescope, X-ray telescope, gravitational wave detectors in space. But NASA was developing antennas also for these purposes already back in the days. And they had small models again, and they also had numerical computer models. And this was the project they had, which is very fun, I think. It's very nice. They had a very compact folded antenna that you put it on a spacecraft. The spacecraft goes in space, and then it deploys the antenna that very quickly, bloop, opens as an umbrella, And you see here how it will work and how it will look in the end. And what Katherine Johnson's worked on was the control system of this antenna, because on board of the antenna and other things, you want automatic systems that basically respond to your inputs. And it's a huge challenge because you have a heavy antenna floating in space around the Earth, for example, and you want it to point to the right direction. For example, you want to communicate to one of the shuttles, it has to point towards the shuttle, or you want to, if it's a telescope, you want to observe a specific object, it has to look at the object. And it has also to be stable again, right? It shouldn't fluctuate, because when you're on the phone, you don't want your communication to be intermittent, especially if you're talking with somebody in space. Or for example, you don't want to think that the source you're looking at is variable when it's not, or maybe you cannot see the variability because you think is the variability of the source. And among these challenges, there is even more that you want to do all these things in the most efficient way possible. Because the more you use things, the more they can break, or at least the sooner you run out of fuel, for example, compressed air, on some of the engines that would turn the antenna, no? And to go in space and fix things or replenish things, that's difficult. So you have to be efficient. And of course, you want to be quick, right? Because you want to do it as soon as possible, especially for communication, perhaps, right? If there is an emergency, you want to communicate very quickly. So the answer to that is control theory, which is another branch of mathematics. It's again quite complex. I cannot claim I understood it much, but Katherine Johnson worked on it and she could deal with it. And in a nutshell, what it was is like your thermostat in your house. You input some controls. For example, you set the temperature of your house, and then the controllers respond. On the antenna, it would be gyroscopes that turn the antenna, or it would be the heater in your house that starts warming up the room. And then the automatic system starts measuring the current status. For example, again, what's the temperature now of the room? And it calculates where it should be based on its program and the input. And then it checks if there are differences and corrects it. For example, the room temperature is rising too much, then the system says, oh, I expected it to be colder, but now it's warmer, so I can stop the heating, for example. No? So it sends, again, inputs to the heaters or the gyroscope on the antenna, and this loops goes on until you reach your condition. And this specific bottom part, the calculation of the system that the system would perform, is what Katherine Johnson worked on. And especially the part where the corrections are calculated, because there are different methods to do that. And again, they had to check which one would be the most effective and, correspond the fastest and the less expensive. And again, to go back to the antenna, they were testing different things. These are from the papers, but it's a series of papers. They were testing, for example, where to put the controllers on the antenna, on the mast of the antenna, or on the ring of the antenna, they call the hoop. And they were checking, for example, which position would require more energy or less energy, which one would be fastest, which one would be more stable, no? Less oscillating. And in particular, the paper that I worked on tackled an important thing in science, which is any measurement has a degree of accuracy. It's not infinitely accurate. And they explored, for example, which parameters of the antenna would be needed to be known the most accurate, because if they affected the behavior of the system, then they had to be known very accurately. If they were not affecting so much, they could be known with less accuracy. But they have a series of papers, so they work on very many different aspects on the control system and the control algorithm. And I mean, to me, it's amazing because she could really work on all these different things, because basically she spoke mathematics, which was the language that enabled her to tackle all of these different aspects. So I was very impressed, and I think now it's time for Elena to speak. So I stop.
Thanks a lot, Yuri and Valeria. Let me also share my screen.
If I can interject a comment.
Sure.
I forgot to, I assumed I would introduce all of you in turn. So let me just mention that Yuri has a master in astrophysics from Padua University. It's also the town where I was born, so sort of relate. Then a PhD from the Pannenkoek Institute in Amsterdam. Then he worked in Princeton and Southampton and joined the Universidad Nacional Autónoma in Mexico City, where he sits right now, where it's probably warmer than -7 in Berlin and the same in Munich, probably. Okay, and then Elena Sacchi has a PhD from University of Bologna, and she works at the at the Leibniz Institute for Astrophysics in Potsdam.
Thank you. Okay, let me reshare my screen. Yes, so thanks a lot, Valeria and Yuri, for your talks. And I think we really saw how much Katherine Johnson did in her career. And I want to focus a bit more on the modern applications of her calculations that are still very useful to modern missions. So, for example, here you see Atlantis, which is the last space shuttle mission from NASA in 2011. And on the left, you see the trace of the shuttle re-entering in the Earth atmosphere. And on the right, you see the actual landing. And behind all this, there is a lot of calculations, of course. So there is a lot of geometry, a lot of trigonometry. And one of the reports I studied and researched for is actually the calculation of the angle that we need if we want to make a satellite or shuttle land in a specific point on the Earth's surface. So basically, this involves, calculating all the trajectories and the projections of the trajectory of the shuttle on the Earth's surface. And you need to take into account the fact that the Earth itself is rotating. So if you want the satellite to land in a specific point, you need to take into account its orbit and the movement of the Earth. It's still very actual. And indeed, the way shuttles re-enter on Earth today is based on the same principles. And of course, the three main parameters to consider are the deceleration of the shuttle or satellite, the heating, and the landing accuracy. So basically, it's like when you want to play skipping stones on a lake. If you throw with the right angle, you're able to make a lot of bounces on the surface of the water. And in this case, we want the opposite, of course, because we want the shuttle to enter the atmosphere, which is this dense fluid we need to take into account. But of course, if you enter with a too sharp angle, the risk is just to burn the object, in this case, the shuttle with its equip. So there is a very fine balance between these two aspects, and this is called the re-entry corridor. So this line you see here, this sort of strip you see in the figure, which is the exact region you want to stay in, not to what's called overshooting or undershooting. Of course, the deceleration is very strong. So this impacts, for example, the construction of the structure of the shuttle itself. And actually, modern materials and structure can withhold hundreds of the Gs, so hundreds of times their weight. But indeed, human beings can only withstand about 12 Gs just for a few minutes. So about 12 times their weight. So this, of course, puts a lot of constraints on the deceleration and the re-entry trajectory and the procedure. And as we mentioned before, of course, another factor is heating. because the shuttles can reach more than 1500 Celsius degrees when they re-enter. And there are very interesting programs that I researched for this report that use now near-infrared imaging to monitor the temperatures of the shuttle re-entering. So, for example, here you can see images from the hypersonic thermodynamic infrared measurements, which was the first program NASA implemented using near-infrared sensors. It's super interesting to see how they use these images to calibrate actually then the programs to re-entry. Here you see on the top like a single image, and you see the shape of the shuttle and the most heated part on the wing, and then a zoom on the wing, and then they average different frames to increase the resolution. So her calculations still have a huge impact on what we do today in space missions, and I think this is just amazing, and it really shows like her mind, not only her impact on like as a group of a minority, but really her incredible mind. And then the landing accuracy is also important, and for this reason, Apollo missions were designated to being able to land on the water, because we have the Pacific Ocean, and that it's huge. So of course you need still to be close to the ships that will just recover the shuttle. But it's much easier if you have a big surface where you can land. It releases a lot of these constraints you have on the orbit and on the accuracy when you land. And then I just wanted to talk a bit about how we managed to basically fund this project. So the work itself made by the three of us and Alessandro was all voluntary, but then we needed funds to actually print and ship the book. So this was made through a Kickstarter campaign that lasted a month. We had the endorsement of a few institutes and some associations that you see here that basically supported our project by spreading the voice and, spreading this to their communities. But the real support was by these 120 people that actually contributed to the campaign and made it very, very successful. So a huge thanks to them. Of course, they received the book, and the biggest contributors actually also received a Python code we made that can be used to basically redo some of Katherine Johnson's calculations, and this was mainly wrote by Yuri. So I think this is super cool. Also, you can put your numbers and make some calculations and feel a bit like you're also contributed to NASA's missions. As Yuri mentioned, it was a lot of work even just to go through the reports, because here is an example, and like many of them are publicly available on NASA's website, but they're basically a photocopy of the original reports. Here you can see the quality, and also some of the plots were very old and some are handmade, so it was quite a challenge even just to go through the reports themselves. And then of course, as Valeria mentioned, we wanted to put a little of context and how they're connected to modern missions. So it was a lot of research and a lot of time. And then the retyping and editing was made by these three people in our team. And as Vincenzo mentioned, actually the original reports are there just with updated graphics and plots, and they're in yellow with this yellow stripe in the book. While on the right you see an example of our commentary. So all the research we made on top of the reports themselves. And we received very nice feedback both on the book itself and on the whole project, and this gave us the energy to keep going and keep believing in it. And in that, yes, we have this, I think, very awesome book that shows the work we put in. And just for a minute, I want to I want you to hear from Katherine Johnson herself. This is an interview she made a few years ago. So I will just play this.
I wonder what you think about that kind of research and whether there are gender differences in how we deal with math.
I think the difference is in the desire to learn. Girls, I found myself very inquisitive. I wanted to know what was going on and why, about whatever was the subject at the time. It was important to me to learn why. Girls, some of them are reluctant to ask questions. They feel that they're just being curious, but if you want to know, you ask a question. There's no such thing as a dumb question. It's dumb if you don't ask it. But girls are capable of doing everything men are capable of doing. Sometimes they have more imagination.
Yes, so as you heard from Katherine Johnson and also from Valeria before, what we really want with this project and all Quaternion's project is to promote STEM subjects and education for everybody, because unfortunately there is still a lot of imbalance in science for women, but also like for minorities, and Katherine Johnson was both. So really what we want to do is just to make this a bit more even as much as possible with science, with our work and with what we know and with our knowledge. So I really want to thank my colleagues for this project we made together. It was so interesting, both intellectually and also on everything like involved in it. And I want to thank you all for listening and for being here and being part of this.
Thank you, Elena, and thanks everybody. It's really fascinating. It's been really fascinating. And the book is, I mean, as we discussed when we were preparing this. I mean, I did my share of editing and doing figures and writing things, and it's a lot of work and an excellent work, I would say. So I have a few questions myself. So let me just. So you mentioned the Python code, so I would just wonder, perhaps, I don't know, perhaps Yuri can answer, but it doesn't matter really. So, of course, many of these figures were, sort of photocopies and not very accurate, not very readable. How did you go about redoing them? Did you recalculate things, but at least the relevant things to do the figures, or how did it work? So, or maybe the question is, did you redo most of at least some part of the calculations to produce the updated version?
Okay, answer. No. In the commentaries, some figures are remade with the codes, but the original one is really the Quaternion team. They went on the original ones. They really checked everything and they remade them very, very nicely, very well done.
Like in the old times, people would bring a plot on a millimeter paper and somebody would draw it very carefully.
It's true to the nature of the work.
Yeah. So maybe I can stay with you. So this so about the antenna paper, the 1986 is the real year, or is that published later, but worked on earlier on?
It's done through a range of years.
Okay.
So the last one I think was published in '86, but the work has been going on for a few years.
Would it be fair to say that this is let's say a rigid body, complicated rigid body calculation with fluctuating parts? Is that what it is, more or less?
Yes, but it has modes, so it's not fully.
Yeah, so it will. Yeah. So it's a rigid body, but actually with moving parts, which is it makes it non-rigid anymore. Okay.
Exactly.
Yeah. So that's. I mean, yeah, it's really fascinating. I have to. So actually, okay, Elena, I think made us this little gift of hearing this heartwarming Southern accent of Katherine Johnson. She actually, it turns out she died 3 years ago. 2 years ago, it was 101, so a long, productive life. Actually, Elena, I think, also edited another paper in the book that has to do with the gravity model of the moon. So, we simpletons, that do condensed matter, okay, we think of gravity like a point thing. So it's a 1/r potential. So how does this? So what is it about this gravity model? Is this something like, I mean, non-spherical content of the gravitational potential as you orbit a body which is not a sphere and it's irregular? Yes. Is that something like that?
Yes, basically it's this approximation through spherical harmonics, and then a calculation using different number of coefficients for the spherical harmonics to approximate basically the body of the moon and the shape of the potential of the moon. It's also super interesting why we were researching for this. We found out, for example, that at the time, people didn't even know that the moon was solid. So some people actually strongly argued that the moon would be just this soft surface, and that a shuttle would just sink when landing, trying to land or to arrive on the surface of the moon. But yeah, basically the main approximation was that, and then it was I think it was one of the first times when they started to use also what we today would call actual computers, so digital computers. So some of the most complicated calculations were made both by hand, by Katherine Johnson, and then also remade on the first IBM computers.
Yeah. So, well, apparently, no, because I didn't, you never think about it, but it's an important problem. So it's not just, some little non-spherical features that are not so important, but they can be substantial, right? So especially, I mean, okay, the Earth is rather non-spherical, and it has peaks and stuff and holes, etc. And on a reduced scale, the same applies to the moon. So I understand it was important to actually mimic as much as possible on the presumed trajectory of the landing.
Yeah, and this indeed was based on many other missions that were just going around the moon, trying to collect data, basically. So from the orbits of these smaller satellites around the moon, so that's why it's called small arc calculations. And it's also super interesting how they were trying to communicate, between these satellites using the Doppler effect. And sometimes they did another satellite, a third one, because of if you are behind the moon, there is not direct communication, so you need something else in between. I think it's amazing to see also what was achieved with the quality of the data they had, because now I think we are used to very, very high quality data, even just from space telescopes and interferometers, and really seeing what they were able to achieve with those data. It's I think you really needed to use your mind at the maximum to get the most out of the data.
Yeah, and with those computers, it was little they had. So yeah, so Valeria has mentioned the celestial. So this celestial navigation is actually, it's what you call it on ships, on the sea. But this is really celestial in every sense, let's say. So it's really amazing. No, I just wanted to ask you about the. Actually, there's a question about this. So I wanted to ask you two things about let's say the publishing thing. So one thing is this new project on the Bletchley Park decryptors. What is it about? Is that will we hear a cryptography installment analogous to this one, or what is it about?
Yeah, so I'm not directly involved with the other project, but I know that it is based on a theater representation that was written by I actually don't know the name of the person, but this is a still living person who got in touch with the Quaternion with this representation. So the project will be revolving around this existing work. And again, as now it's becoming some sort of a scheme in the Quaternion publications. Now it will be dedicated to the this team of female mathematicians who worked in the Alan Turing division to decrypt the Enigma machine. And so this is as far as I know, but I'm also very curious about, and I think there is a lot of interest in math, and just the story of it is very fascinating. So I'm looking forward to see the outcome.
Okay. So Yuri, perhaps you can tell us about so I'm just wondering, any of you, of course, could answer. What do you think is the target audience of this book? Because it is a nice book to have. At least it shows off on a shelf. That's for certain. Then, of course, if you are a physicist with some with a decade or so of experience, you can enjoy a lot of or a mathematician. But what do you expect is the target to be? So, would you like to read it, to own it, hopefully? Yuri, or anyone?
Yeah. I guess everybody. I guess it's very broad, no? I mean, Elena, Valeria, intervene.
Only just the introduction is worth the whole. I guess it's worth the price, because it's very and it's very illuminating of the atmosphere and the goings on in the space race. So I just wonder.
I think it's for people that want to know about the personal stories or the social issues, if you want, and as well for people that have more, maybe are more curious about really the science and so on. So like a different level from high school on.
Yeah, I think we have. There's a question from the audience. So Christophe says, thanks for the talk. I was wondering, with the Artemis mission recently, the re-entry happened with a bounce, like a skipping stone. Was this also the case for the Apollo re-entries?
Yeah, I can answer to that. Hi, Christophe. To my knowledge, no, this was the first time it was tried. So I think with the Apollo mission, it was never tried. But now with more accurate control systems also on the spacecraft, they tried this because I think mainly it helps to reduce the actual heating with this sort of maneuver with a bit of skipping and then going back to landing. But I don't think it was never used in the Apollo missions.
Okay, so yeah. It's been a very interesting, almost an hour. And so I would like to have any comment of the three of you about the general project and about your programs for the future. Maybe the next project that you will be directly involved in, perhaps. Let's go in reverse alphabetic order. Okay.
I can start with maybe a general comment for the audience. Is that like I often hear a little bit of a criticism, right, that there is actually a lot of finance that goes into space science, and it is fair to say that on Earth we have even more difficult problems that needs to be solved more urgently. And I would like to I think it's a correct context to reply to that, is that actually, with this book and the story, like the calculations of with the figure of the Katherine Johnson, the space science inspires, and it's even with the science that we discussed today, it shows like it leads the humanity to a greater progress, right? Whether it's space antenna, whether it's space navigation, development on new techniques, new technologies to be used, whether it's in space or on Earth. And I think it is, I know it's far, I know it's not directly affecting any of us, but it is really important to, to research on this and to get finance. So I hope you share my opinion there.
Yeah, I think so. Well, in fact, I guess not by chance many agencies are called aerospace, because of course aeronautics and space are connected, and nowadays there's a lot of technology. Probably space, quote unquote, is the field of general endeavor that produces more technological progress than any other field of, except for probably for material science. That is, well, it's an applied field, let's say, devoted to just doing that, but let's say as a byproduct of general scientific endeavor, that's probably the most productive field, I suppose. Elena.
I definitely agree, and I want to stress in a different topic, which is how important I think is science communication and outreach. So with this project, we really want to reduce the gap between scientists and non-scientists. And actually, I saw there is a comment about what is the target for this book. Yeah. The idea was basically to have people who have a bit of like math and scientific background. So say, someone doing a scientific high school, but still not like skilled enough yet to understand these reports. So the idea was to sort of bridge this gap. And I think, in the modern world, there is so much information and so much misinformation. And I think it's really our responsibility as scientists to be closer to people, because we receive funds from governments and basically people taxes, and I think it's our responsibility to give this back to them, so to help them understand the core of science, which is, I think, the most shared thing that there should be. With these projects, I think this really goes into this value I think we all have of really trying to communicate what we do and what other scientists do.
Yeah, definitely. I always get the impression that, this book definitely escapes let's say, the tendency to flatten the level of discourse to the ground. Meaning this is a high level, scientifically complicated, well, fairly complicated for the average reader, let's say. So this is, let's say, outside, but there seems to be a tendency, I perceive, to always trivialize things, to, exemplify complicated situations or complicated processes, and, in a way that doesn't really, clearly there is a need for shall we say, popularized science, definitely. But personally, I have the impression, I don't know what you think, but personally, I have the impression that there tends to be, it's mostly popularized and not so much science, let's say, in many cases. Whereas you can tell that this thing here is, there's a lot of science. Maybe it's not, it's a bit on the high end, let's say. So it's a bit, so the target is pretty ambitious. But, so anyway, I don't know what you think about this, but it's, I would like to see more books like this where, you have to bang your head against the wall for a while to understand what's going on, rather than, the usual tribe that's not really, doesn't really add very much. Anyway, Yuri, you're up.
Well, I think Valeria Nela has said the most important things. But I mean, one thing, maybe it's a comment on the experience and maybe the goal. I mean, in a sense, also the idea of the book. It's so Valeria said, for example, that it's nice that people complain about space science. It says, oh, there's no more important problem, but it can reflect on what we did. And I think one idea of the book was very nice, because instead of being a bit abstract, it showed in fact the value of the work of people. And I mean, it shows the fact, and so the fact can show that basically anybody, independently of minority or whatever, they can do great contribution. And I think it's a very good way to bring about this message, because I mean, it's facts. You can't say, oh, you're just talking in general in here. No, it's here. You can see it.
Yeah, so it's real results done by real people. Actually, I find it very fascinating to read. I happened to read some papers about because of the fusion thing recently. There's this announcement. So I read something about the development of the thermonuclear, the super bombs in the early 50s, and it's fascinating to read. These were actual people who did actual scientific work with additional, let's say, ethical or problems that of course, maybe are less problematic with space science, although even space science could be used for say, for purposes that are not especially desirable, but mostly they are not. One thing I would say about, I don't know if people complain about space science being costly. Of course, it is costly, but I don't know, as a physicist, being outside, say, outside particle physics, as I'm outside astrophysics, I'm okay with astrophysics spending money more than with particle physics. That's just my taste, perhaps, but I happen to be in the board of the European Space Southern Observatory. And so, I mean, there's a lot of money spent there. It's a lot of people working and so on, but still, I think there's no shortage of interest in space science and in astronomy and astrophysics in general, although it's very, especially I would say from the layman. For example, I have a couple of telescopes. I consider myself, of course, a layman. And what you do is probably less rewarding, because you do a lot of complicated stuff and a lot of computing, a lot of modeling, a lot of data processing and so on. So you don't go outside and look into the telescope. So I think people are rightly fascinated by this. So anyway, again, my thoughts. Okay, I think we have no other questions, and if you have no other comments or messages, but you conveyed a few interesting messages. Actually, I think we can stop here and so reconvene at some point when there's a new book or a new
next book
contribution. Yes. from your, doesn't need to be from Quaternium, of course it would be nice, but any other thing, yes, from your side.
Yeah, and thanks a lot to you and the Institute for allowing us to share this project. Thanks so much.
It was very nice, and hopefully, because we have, there's the embassy and the Cultura are related, but not mapped one-to-one, one on the other. So we can imagine in the future to have some actual physical event in the embassy about maybe related topics.
For sure.
Okay. Thank you. It was a pleasure.
Thank you.
Thank you.